right? When we have done measurements, okay, we have discussed about errors, and then the last part is measurement, and then you get data. So from the data, probably you can do F test, T test. You start with Q test, F test, and T test. Okay. So after that is done and you are confident on the data, we have to make sense of the data. So in order to make sense of the data, sometimes it's not necessary to have calibration plots. Yeah? It's not necessary. It is enough just a statistical analysis. But if you are developing a series of measurements, if you are producing, if you are doing a series of measurements and you want to correlate, the word is correlate, the parameters, you want to correlate the parameters or you want to see the changes between the parameters, then calibration graph is very important. Whether the relation between the parameters linear or non-linear. Okay, so we are used to y and x. Okay, so y will be the one that is okay. Just will be the dependent. Okay, dependent on x, so it will be dependent variable. Dependent, right? And x will be the independent one. Why? Because we prepare. Okay, we prepare the concentration of standard solution and we expect the determinate error is not there. Okay, there is not really so much error from the preparation. Okay, so now we plot the, or you can just do a calculation, not necessarily you have to plot. We need to identify the correlation. First, of course, we have to find out the, sometimes they use this as B, this one as A, yeah, because the slide is prepared by someone else before, okay? I'm actually using their slide sometimes, it's okay. So this one represents the slope of the calibration plot. And this one represents the intercept. Okay. So as I have showed you last week, you can calculate or you can come up with this linear equation by calculation using formula, the least square method. Okay? Or you can just use any spreadsheet, okay, to get the value of M, to get the value of C, and from there you can identify the unknown sample. Okay, you can identify the concentration of unknown sample. So this method is what we call as interpolation. And somebody asked whether we can do extrapolation. It is quite dangerous to do extrapolation because sometimes if we're not if we didn't really study the concentration, it might be linear and it might not be linear after certain concentration values. Okay, so based on my experience, what we did is we try a few sets of calibration. Okay, a few sets of calibration to look at the linear range. Yeah, so once we have identified the linear range, then the extrapolation cannot be that far from the linear range. Yeah. So after that, this is the simplest one. And then comes the complicated calculation where you start to have to calculate the standard deviation for the slope, standard deviation for the intercept, and also standard deviation for the y, because y is dependent variable. Okay, so there is error as well. So we have seen the formula. I've shown you the examples, how to calculate all these standard deviation for slope, for intercept, and also for y. Of course, they are quite complicated, but as I mentioned, of course, during assignment, you're not supposed to be memorizing anything. You can just open any resources. Okay, so it's not really an issue about the formula if you are to calculate. And during final exams, okay, the formula will be given to you. Okay, so you don't have to worry about memorizing the formulas, but you have to know how to calculate. Yeah. Before this, I was not in Malaysia, so the final exam was conducted online. But this year, this semester, your exam will be at the end of, is somewhere in end of January, I think, or February. It will be physical, yeah, face-to-face exams. Don't worry about it. The formula will be given to you, but um, um, I will try my best to allow everybody so that you can plot Excel, yeah? Using Excel to do the calculation, okay? But it has to be very limited. Well, you can't just be ethical. You don't check on the notes or whatsoever, but just use Excel. So that will be in future, not to worry right now, okay? So now, just to recap, we need to know, is the trend linear? Because from there, I forgot about one more parameter, is the correlation coefficient. Coefficient. So R is between 0 to 1. Okay. So R can also be calculated using formula. Yeah. It's a looks complicated formula, and also can be generated from the spreadsheet. Yeah. Which is much easier. So if you can get R approaching 1, means that the y and x parameters, they are correlated well. Whereas if you have R approaching 0, means that the y and x variables, y variables, there's something wrong with the data. There's something wrong with the data. So this is actually the ultimate aim when we are constructing a calibration plot, other than identifying the unknown sample. Yeah, because we need to have a good R first, a good correlation first, before you can use to identify unknown sample from the calibration plot. Right? So remember, the points on the plot can contain error. So what I did, yeah, we on the plot itself, we can calculate the error bar for each point. So that gives us some confidence whether the data is good, if the error bar is within 5%. So if beyond 5%, then you have to be cautious. Yeah. Okay. So when we do analysis, it's all about errors. Okay, that's why we have to be concerned about this standard deviation. Okay. Confidence limits, remember, I think from the second lecture, I think the second lecture that I mentioned that you have to know how to calculate confidence limits. Okay. Because it's very easy and you can look at the example in, it's either in GD Christian or any other reference that you can reach, right? Yeah, right. The unknown also will have its own standard deviation and also confidence limits. Within what limits is acceptable, right? So today we are going to discuss limit of detection. So I'm just going to just briefly show you some of the formulas. Remember, so this is our correlation coefficient. So there is some difference with regression. Okay, so I will show the differences of correlation and regression at the end of this slide. Okay, this is about the value of R just now. Okay, all these examples, I think I have given you the Excel file. Probably the pages has changes because I add on some more slides. So you have to match which Excel tab that is a match with the question. So please do that. Okay. Right. So I just want to recap back. This is what we have done before during last week, showing an example of how calculation using least square plots, least square methods. Okay. So these are the data and this is the formula to calculate slope, which is M, and to calculate intercept, which is B. Okay, so there is a bit of calculation to be done because you have to find the X bar, okay, and the summation. Okay, all this can be done. And also you can calculate R from this data. So in the end, you can, of course, this is the value of M and B. B is the intercept, okay? And in the end, you can have the linear equation, okay? Y equal to mx plus c. In mathematics, we are used to this for the linear equation. And from there, you can calculate the sample, the unknown concentration of the sample. So this is by using calculation and also can be done by plotting in Excel. So this one has been solved and you can find it in Excel file. Okay, so you can see the difference when you have R totally chaos, when you have R close to 1. Okay, so this is very important, okay, to evaluate whether you can use the calibration or not, right? Okay, this is the same formula from the slide just now, from this slide, okay. So I just skip this. So remember about the standard deviation for Y variable, standard deviation for in this case, B is the slope, okay. Standard deviation for intercept, okay. They're all just something that you, if you need to, then you calculate the standard deviation. So this one problem is related to slide 16, the riboflavin just now, riboflavin. So this is how we calculate the standard deviation for Y, for the slope, and for the intercept. So just use the formula and we can get the values. Same goes with the unknown sample. Okay, it's a bit complicated because of the we didn't discuss about the propagation of error. Okay. Okay, so if we are to use a very detailed one, then I never use this complicated standard deviation for slope, for y, and for an intercept, and for the unknown sample. Okay, I never use this. All right, so this one also has been solved for you. Okay, all right. So the regression line is actually when we are considering errors. So I don't know, I never use a regression line. So the one that has taught this courses really is a yeah, has been teaching statistic quite long. So, but I never use this one, so I don't know. But probably if you need to, then you can have this regression line. But the formulas are all there. Hmm? All right, so let's look at the the difference between correlation and regression. Okay, so correlation, the most commonly used techniques for investigating the relationship between two quantitative variables are correlation. Okay, so also regression, but uh, the most common one is correlation. So correlation quantifies the strength of the linear relationship between a pair of variables, usually two variables. When we have two variables to be compared, then we use correlation, the R just now. Whereas regression expresses the relationship in the form of equation. Means that more regression you can use for more than two variables. Yeah. So let's say if I have developed a new method for detecting cholesterol. Okay, so let's say new method, which is I put as y-axis, and then I also use the same sample, okay, standard method to identify just now is the uh, cholesterol, but the same sample I use for my new method and for the standard method. So if I plot y, x, okay, the R will give me an indication whether my new method is correlated well with the standard method. This is what we want, okay? If it is not correlated well, means the R value is very low, lower than 0.9, then probably my new method is not that good, or I have to repeat some data, okay? So how do we see it? It's correlation. If I just want to change the y-axis into x-axis, and this one is y. I define it as x, still standard method, and y new method. You still have the straight line, okay? Still, you can value the correlation using R. So that is correlation, okay? But if it is regression, you cannot do this. You cannot change the axis. Because in regression, we are talking about multiple variables, okay? So if you plot this way, x versus y, or y versus x, it's going to be different, okay? So that is a big difference between regression and correlation. So until now, as a chemist, we do correlation, okay? Uh, probably somebody who does like biological sample or plants, probably they have a lot of parameters to be studied at one time. Yeah? So probably they do correlation. So this is just to show you the formula, okay, for correlation coefficient. Okay, I think we have it in the previous slides. Okay. Uh, yeah, looks complicated. All right. But I think this is the one. All right. And let's say if we have r squared, just now it's r, okay? And then r squared is coefficient of determination. So I think both are can show the correlation, whether it's correlation, a coefficient, or coefficient of determination. So it's just value of r is squared. So this is usually generated from the plots. Okay. So if the one, these are the one that we have discussed and extended to some correlation and the difference with regression. So I hope that has given you ideas, or you are very familiar with limit of calibration plot and things that you have done this many times. So this information is for those who haven't. Okay. All right. So limit of detection. Why do we need to know about limit of detection? Because of the linear range just now. Okay. Remember the linear range. So we can do unknown sample, but how low the concentration that we can go. Okay. So if we bought instruments, yeah, for example, AS, atomic absorption spectrophotometer, or ICP, okay, usually what we question the supplier or the companies, okay, what is the detection limits, okay, whether it can go down to part per billion level, okay, for certain metals, because there is the needs to be to measure down to the very low limit. Yeah. So this is very important. Yeah. In any protocols or new methods being developed, because this is quantitative. Yeah. Analytical chemistry can be qualitative, can be quantitative, but most of the time we are measuring quantitative value. So if we are to analyze certain sample using that particular method, we need to make sure that the sample, the analytes in the sample subjected to that method is can be measured using that method, using that machine. If we know already that the limit of detection is a bit too high compared to the analytes in the sample, then it's going to be useless. Yeah, it's going to be useless. Of course, the more sensitive means that the lower detection limits, usually the instruments is expensive. Yeah, that's the ultimate, the lowest that we want to identify the concentration. But if you are developing a new wet chemistry method, okay, by using calibration plot, we can identify the limits of detection. So if you look at the definition, concentration of the analytes, that gives a signal that is significantly different from the blank. Okay, so blank is we can consider solvent without the analytes. Yeah, or probably remember about standard addition method that I mentioned before. Okay, so probably the matrix, only the matrix diluted with just solvent. Okay, so sometimes we have to do spike. Yeah, I hope I never explained about spike before. Yeah, spike sample. Yeah. And yeah, I didn't discuss about spike sample before. So we have to discuss a bit. Probably I can go back probably to talk about spike sample. This is the formula for limit of detection. But you can find actually different formulas as well. Okay. So for example, I also come across this formula, but I usually use this one. Okay. I will explain the formula, but this is also another formula. Okay. So what's the difference? It's not really a whether you start. Yeah. Okay. Let's look at this. Let's look at why. How do we get this? So this is the calibration plot. Okay, y and then x. Okay, but the formula is y 3 alpha. Okay. Y beta gamma. Okay, I usually use this y alpha plus 3 beta. Okay, if you look at here, is gamma plus 3 standard deviation. Okay, this is what I usually memorize, alpha. And then beta, it stands for standard deviation. Standard deviation, deviation of blank. Okay. Remember what is blank? Blank is no analytes. Yeah, no analytes. Only matrix. If you are using standard addition method, if you're using not the standard addition method, so it's just a solvent that you use to dissolve. Okay, so we have to at least take 3 measurements of the blank. So what is alpha? Anyone? I'm sure that some of you has done this. Asma?
I don't remember.
Okay. Uh, the formula, a formula that's increasing in usage. Okay. So LOD, Y, it is actually not Y, it's gamma. Okay. I don't know. So, okay. All right. So this is actually the reading, the Y reading from the blank sample. Okay. So, so what actually the LOD is not yet the final concentration, but we are calculating the value of Y, which is the blank reading. Okay, I usually use alpha, the blank reading plus 3 beta. Beta just now is the standard deviation. Okay, so what will the value that you will get is the value of Y. Okay, means that, okay, let me have another slide. Let's say I'm using UV with spectrophotometer. So the Y will be absorbance, right? It can be reflectance, it can be transmittance, depends on the signal that you are generating from the measurement. So this one is usually concentration. Yeah? Right. So when we're talking about LOD, we're talking about finding Y, which is the absorbance. Okay. So blank reading, absorbance of the blank plus 3 standard deviation of the blank reading. Okay. But you still don't consider this as the concentration, because usually the limit of detection that we want is in a form of concentration units. True? So let's say I just name this Y. Okay, so once we calculate this, okay, we get a new absorbance, right? Okay, so remember the calibration plots will have the linear equation. Okay, so we put the Y absorbance that we calculated from here. Okay, and from there we can calculate the X. So X is usually we consider the limit of detection. Okay, because we want to know how low the concentration that can be detected by that particular method. Okay. All right. So let's look at example. So this is another formula. Okay. So LOD here. Okay. The LOD is concentration give a signal that's above background signal by 3 times the standard deviation of the background. Background usually is the blank. Okay. All right. So it's similar to 3 beta just now. Standard deviation of uh, blank, okay? But this time is over slope, yeah? Right, so yeah, I think I have found a few formulas. So I don't know. Yeah, statistically, I don't know whether which one is suitable, but I use the alpha plus 3 beta, okay? All right, now let's look at an example. This one also does not really use the same formula, but at least you have some bets from here. A series of sequential baseline absorbance, okay, are made using spectrophotometric method to look at purity of aspirin in tablet using a blank solution, okay. So so this one is blank solution first. So the absorbance, remember we are talking about the absorbance reading from the blank solution, okay, from the blank solution is listed in the slide, okay. However, a standard 1 ppm aspirin give you an absorbance reading of 0.051. Remember, absorbance does not have any unit, it's arbitrary unit, yeah. So what is the detection limit? Okay. So remember the formula is Y equal to alpha plus 3 beta. So alpha is supposed to be the reading of the blank. Right, so let's look at the questions. Do we have standard deviation? We have to calculate. The data is being given, has been given. So the standard deviation of the blank reading calculated from the data, okay, it's already calculated, so it's plus minus 0.032. So that is the standard deviation, which is the beta. Okay, and the mean of the blank reading, okay, the mean of the blank reading, so which is supposed to be alpha, okay, is 0.04 absorbance unit. Okay, but this is a different style. So the detection limit is that concentration of analyte that gives a reading of 3 alpha just now, 3 beta. Remember, 3 beta above the blank signal. The net reading, okay. But there is other information, which is 1 ppm, give the absorbance of 0.051. So we need to imagine this is the calibration plots, okay. And blank is the intercept, probably is 0.04, okay. So the 1 ppm data has to be subtracted with the blank, and this is the actual reading for 1 ppm solution, okay. So this is a bit weird because this is what we call as proportional. Yeah. So uh, so it's quite very straightforward. 1 ppm will give you the reading of 0.047. Okay. So the 3 beta 0.0096 will give you 0.096 0.0000 over 0.047 times 1. It's actually proportional. Okay. So meaning that 3 beta, in this case, there is no alpha. The limit of detection considered is just 3 beta. So as I mentioned, there are multiple ways of calculating. So it is considered here 3 beta. I assume it's actually 3 beta over sloped. But here, since it is has been subtracted with the blank, so the m is actually equal to 1. Okay, since originally it is here, but since the value of 0.051 has been subtracted with the blank value, so if you replot, it's actually the intercept, yeah, probably m is 1, I don't know, but they just use 3 beta. Okay, and then from there you can calculate the the 3 beta concentration is 0.2 ppm from the proportional. I don't know, the word is, let me insert the one. It's not that difficult. Where is it? 0.047, okay. 0.047, this is the absorbance reading, okay, is for the 1 ppm concentration. This is known from the question, okay. And from that 3 alpha, 3 beta is 0.0096 absorbance. Is if we calculate, it is like this, 0.0096 over 0.047 times 1 ppm is actually 0.2. Am I correct? Yeah, 0.2 ppm. So this is the limit of detection. Okay, but the what do you call, the interpretation from this, the limit of detection is only considering 3 beta. All right. Okay. Question? Right. So now we also have LOQ. Yeah. So the precision at the detection limit is by definition 33%, but for quantitative measurements, the LOQ is generally considered to be the value 10 times standard deviation above the baseline. So approximately 3.3 times the LOD. Okay. So LOQ is a bit high. I'm not really familiar with LOQ because I don't usually do HPLC. Anyone has experience using HPLC or any chromatography? Anyone? I'm sure. Yes, Asma.
Yeah, I do.
Okay, which one do
Yeah,
you
I agree.
actually, yeah, important to you, LOD or LOQ?
I think I think both is important, but LOQ is important for our quantification
Hmm.
uh, limit.
Quantification limit, yeah?
Mm.
All right. Because in my line of research, we usually prefer LOD because the one that we we want to achieve, which the lowest concentration that can be detected. But I don't know. Probably we can discuss that. So the limit of detection, this one, I think can be referred back to the Excel, right? And this is the whole thing. This is at least one example that gives you that use the uh, alpha, sorry, alpha plus 3 beta. Okay. This is the example that really use alpha plus 3 beta. So if you look at here, the LOD in terms of the reading of Y, fluorescence in this case, also there's no unit for fluorescence. It is arbitrary unit as well. So we look at, uh, yeah, Y beta, where's the reading? 1.52, which is around here, okay? So 1.52 plus 3 beta, you have to calculate the standard deviation, but it has been calculated for you, which is here, okay? Okay. So from here, we got the value of fluorescence, okay, intensity, okay? So this is fluorescence intensity. Now we need to calculate the X, which is the concentration, okay? So how do we calculate the X? Because the linear equation has been given to you, which is Y equal to 1.93 X plus 1.52. Okay. So X uh, is Y minus 1.52 divided by 1.93, right? Okay. So Y is calculated here is 2.83 minus 1.52 over 1.93. Yeah. So now we get the X, which is in concentration of 0.67 picogram per mil. Yeah. So that is the lowest, supposed to be lowest concentration of the analyte that can be detected by this developed method, fluorescent method. Okay. So I have shown you a few uh, formulas. So, so this is, okay, the first formula. And this is the second formula. Okay. And from this example, is actually another formula. It's just Y is the limit of detection starts from 3 beta only. Okay. And then the final one, that's the final example is using the alpha plus 3 beta. Okay. I try my best to make it clear, but don't worry because this also can be calculated using Excel. Okay, so don't worry. So you can see that all these can be calculated using Excel. All right. Okay. Do you remember about the standard addition method, which is very important? Okay. Usually we need to be well versed on this. not just the standard that we used, because we are usually working with crude samples, not really standard samples. Okay. Now the next one is the ANOVA will be taught by someone else starting from week 8. The week 8 will be your mid-semester break. Oh, no, week 9. Week 9 will be your mid-semester break. So week 8, somebody will take over teaching the ANOVA for 3 weeks, I think, for 3 weeks. And then after that, you'll be learning chemometric for 5 weeks. So my lecture will be this one, and next week, week 5, week 6, and week 7. Okay, so ANOVA will be somebody else. So what we're going to do from 8 to 9 is for you to be separated into groups. Okay, so this is the first group activities. Okay, what you will do to get to know your group members, because the same group will be used for the second assignment, group assignment, but this is just a practice. So this is for room 1. I will share this slides once you have the groups in after this. So you can just have a look. So how will be presented? You have to, of course, discuss. There are, I think, 18 of you, divided into 4. Some group will have some extra members probably, or less member. You have to come up with a slide together. If you're using spreadsheets or any origins or whatsoever, you have to paste it, okay, on the slides. Okay, calculation also on the slides, and you have to present it. Yeah, you have to present the calculation. For example, if you look at these questions, if to be you have to explain the conclusion. Okay, to be comprehensive, you tested the sample. Okay, all right, and then okay, this one not so much. Let's say this one also. Okay, you have to present the data, you have to present the calculation. Don't just show the calculation, but present it. Okay. Right. And this is the room 4. So you can see that it covers all, almost all our, what we have discussed. Yeah. So if you look at room 2, you have developed a new method. You need to, okay, and then you have standard material. Yes, you do not want to give critiques on the many using the data, compare method to the accepted method. Do your results agree with the accepted method? Now it is based on you, what method you want to use. Okay, but this is based on let's say you are doing the analysis in the lab. Okay, why you need to do F test first, or you need to do Q test first, you need to do T test first before the calibration. Whatever that you need to do before drawing the conclusion. So don't just jump into one statistical analysis. Think about it. What you need to do first, whether you need to remove some data, or whether you just think that the data is good enough, and then, well, you have to look at the precision first, and then the accuracy first, whether you really have to plot calibration plot, or you don't have to. You have to think about it, okay, before you run the analysis and draw the conclusion. Okay. So if you look at, okay, if it is a calibration curve was conducted, so meaning that you have to show the calibration curve. Absorbance, okay, find the slope, okay, all right. From the data given, determine the correlation coefficient. So this one, whether you want to use Excel, you want to use manual calculation, is up to you, right? But these are all just very minimum practice for you to work together, because the group work, we will work on more realistic, more complicated problem. Yeah, right. This is just an example. This is just an exercise. Okay, so before we stop, yeah, do you have any question on LOD? So everything is good?
Doctor,
Yeah.
regarding the exercise today about the group,
Mhm.
we will find
No,
our
no,
own group,
no.
or you
Okay.
will
Yeah. During the 8 to 9 session, I used the breakout rooms, and this will be, uh, you will be grouped automatically.
okay, okay, understood.
All
Okay,
right. So
okay,
after that is, if you're room 1, means that you have question 1. If you're room 2, so there'll be 4 groups. And then I'll be sharing this slide so to everybody, so everybody will know the question. And I will leave it to you whether you want to continue from 8 to 9 by using your own meeting, whether you want to use Google Meet or whatsoever, is up to you. Or you decide in your group that you want to do at different time. Okay. Okay. But the presentation will be next week. Yeah. Not today. Not tonight. Okay.
okay, doctor.
Right. You need to prepare it properly. Yeah. Using a slide, and then somebody has to be presenting it. Yeah. So please collaborate. I think we have 18 plus. Okay. Never mind. The breakout rooms will help to group you. All right, so let's have a break. Everybody, thank you. See you at 8.
Thank you, doctor.
Bye.